I have this handout link for you as well. So we just got to fill in a few examples there, save you a little bit of time, save you a little bit of writing here. Limits at infinity. You kind of know what this means already. You did a little bit of this stuff last year and earlier this year, but the limit as x approaches infinity and negative infinity means as my x's get larger and larger as I go to the right on the graph, or as my x's get smaller and smaller as I go to the left on the graph, you're still asking yourself the question, the limit is what are my y values approaching? What are my y values doing? So as I go to the right and I go to the left here, we're going up to infinity and negative infinity. As I go to the right and go to the left here, you're bounded by that, like the ceiling and the floor right there. So +4 and -4. That's actually the definition of a horizontal asymptote. Is what's the limit as x approaches infinity and negative infinity. So if you get infinity or negative infinity for the answers, there are no horizontal asymptotes on that graph. But if you get a number for those answers, those are going to be the horizontal asymptotes right there. And we did this earlier in the year, chapter 1, where, as I go out to the right, those y values keep getting smaller and smaller. And here as I go out to the right, it doesn't approach a single number. It doesn't approach it doesn't approach a single number. It just forever fluctuates in between 1 and -1, and you can't approach one single thing right there. All right, now this technique, we're going to review a couple things this section there. This technique, we need to practice this technique for the first part of the assignment, okay? And then I'm going to review your pre-cal shortcuts. And then the importance of practicing this technique for the first part of the assignment, because we're going to use this technique to help us do something later on in the year for something other than horizontal asymptotes. We just need to practice this technique. Then we'll review a shortcut, which we'll be able to use, and then we'll rely on a couple of the graphs. And when we do the graph things, I'm going to give you a method here that we got to be able to do these skills without the calculator. A lot of colleges will take your calculator with, let's say no calculator, in calculus at college there. And then some, and of course on the AP test, we got a huge chunk of that thing without the calculator. So we just got to practice this without that thing and then use it to kind of check ourselves if we need to. But this technique I'm about to show you, only use it when you're approaching infinity or negative infinity. All right, you divide by the highest power in the denominator. The reason is because, look, when I plug in like 1 over a million, 1 over a billion, 1 over a trillion, see how that number keeps getting smaller and smaller? So that answer is going to approach 0. So it doesn't have to be a 1 on top. It could just be like any number. If you have a number over x raised to a power, that's going to be like 5 over a million, 500 over a trillion, where that stuff on the bottom is getting larger and larger. And so that answer is going to approach 0 right there. So we're going to use that technique on these more complicated looking problems. I already have 2 of them filled in for you. Let's just do one together. So here's the technique when I'm approaching infinity. And it doesn't matter when I'm approaching infinity or a negative infinity, I'm going to do the same thing. So I'm going to divide by the highest power in the denominator. All right. So usually, instead of writing divided by x to the 4th, divided by x to the 4th everywhere, I usually just put like a little divided by x to the 4th out here. And then I'm dividing everything by the x to the 4th. So I take -3x over x to the 4th. That'll give me -3 over x cubed. Then here 7x to the 4th over 7x to the 4th just gives us 7. And then 5 over x to the 4th is just 5 over x to the 4th, right? And then I'm going to also divide everything on the bottom by that. And then the x to the 4th will cancel out. All right, and then all you're going to do is you're going to look for this scenario in these problems here. If you have a number over x to a power as you approach infinity, that's like 3 over a billion, that's going to go to 0. 5 over a big number, that's going to go to 0. A number over x raised to a power, all of those are going to go to 0. And then what you're left with is technically the limit of a constant. The limit of a constant is always equal to that constant. So you're going to get -7 over 6 for that answer. Let me talk about a couple reasons where the negative infinity will make a difference. It makes a difference on here because when I simplify everything, I get an x in my answer still. Here I didn't have any x's. Here I do. So that negative infinity is going to make a difference. And it's also going to make a difference on the square roots. And we'll talk about that in a second there. But these are both the same kind of problems. You just get a couple different answers there. Now, notice on this one, I saw the x squared. I didn't divide by x cubed because that's the highest denominator. I divided by x squared because that's the highest power in the denominator. It doesn't say overall. It says in the denominator, what's that highest power? All right, so I divided everything by an x squared. You see my work there. Simplified it, got to this, and anytime I encountered a number over x raised to a power, those all went to 0, and you're left with the 2x. And so here's the difference. When you're approaching the negative infinity, 2 ways you could think about this. One, if you just plug in a negative infinity, like 2 times negative infinity, that's like negative 2 million, negative 2 trillion, where that number is going to keep getting smaller and smaller and smaller. So your answer is negative infinity. Or you can think about the graph of 2x. If that's a positive infinity, that's going up to a positive infinity. If that's a negative infinity, that's going down. As I go to the left, my y values keep getting smaller and smaller, and we're approaching the negative infinity right there. So notice I did the same technique. I just divided by the highest power in the denominator, and then just on this one, it didn't matter because it was a constant. So even if that's a negative infinity, you're still going to get that same number. But here, if you got the x's in there, that's where that's going to make a difference. And then right here, just make sure you develop good habits, right? I don't need anybody putting 0 on the top and it automatically saying that answer is 0, because later on in the year, we're going to get 0 on the top, but we're also going to get 0 on the bottom, and that answer will not always be 0. So for now, make sure that if you get 0, keep going. Make sure you show me that you're getting 0 divided by a finite number, and then you're going to get 0 for that. All right, let's talk about these square roots there. This is a very common thing that students tend to have questions on in the homework, and they kind of mess up, on an assessment situation right there. So if you just pay attention right now, you're going to know how to approach this, okay? So one thing, when I have this, right, when I do the x approach infinity, I'm going to divide by the highest power in the denominator. So right here, I'm going to divide by an x squared right there, divide by an x squared right there. And if I'm teaching this to you in person, I would ask you, how come it was wrong if I divide by an x squared on the top? If I divide by an x squared on the top, then I divided by 2 different things on the top and the bottom. We're supposed to divide everything by the same thing. I didn't really divide by the x squared. I divided by the square root of an x squared because all of that is underneath that radical right there. So then they got to ask you, hey, what's the square root of an x squared? And many of you would say that's just an x, and we gotta narrow that down a little bit, okay? So for now, if you're approaching a positive infinity, the square root of an x squared will just be an x. So now I'm dividing everything by an x to the first power. X over x is just 1. And then right on the bottom, you have x squared over x squared is 1. And then remember what this is going to approach. This is going to approach 0. So now you have just 1 over 1. The limit of a constant is just that constant right there. Now let's be careful here. If you're approaching a negative infinity, let's kind of show you some algebra 2 pre-calc stuff right here. The absolute value, the square root of an x squared is technically the absolute value of x, which means it's a piecewise function. It's equal to x. If x is greater than or equal to 0, it's actually equal to the opposite of x if x is less than 0. Let me prove that to you, right? Real quick, if I show you x equals 5, and I plug that in right there, I'm going to get the square root of 5 squared, which is the square root of 25, which we know is 5. So I started with x is 5, I got 5 back again, so I got the x again, I got the x. But see, now if I give you x equals negative 4, and you do the square root of negative 4 squared, well, that's still just the square root of 16, which is equal to 4. So your x was a negative 4. You didn't get x back again. You didn't get the negative 4 there. So you got the opposite of that x. So technically, the square root of an x squared, it could be the x or the opposite of x, depending on the sign of that original number right there. So because of that, we just got to be really careful right here. It's really, really simple, actually. All you got to do, so when you see the highest denominator, highest degree in the denominator is an x squared, you can divide this by an x squared, divide this by an x squared. I actually got that started for you right here. I didn't even see that. All right, you're going to divide everything by an x squared, and all you got to do is this. If you're approaching a positive infinity, you'll put a positive x right there. So that's what we did here, right? The square root of an x squared with positive infinity is going to be a positive x. If you're approaching a negative infinity, all you got to do is stick a negative x right there. That's it. Keep it simple. Square root of an x squared, you're going to use a positive x. If it's a positive infinity, use a negative x. If it's a negative infinity, and then this is going to give us a negative 1. On the bottom, this is going to go to 0 again. So you got negative 1 over 1, which is negative 1. It just means if you graph this function, x over square root of x squared plus 1, it's going to probably look something like this guy, but the horizontal axis will be a 1 and a negative 1. So it has like a ceiling and a floor. Not all the graphs have 2 horizontal asymptotes like that, but this square root one does. And then we're going to be doing that. So you just got to be a little bit careful if you have the square roots, and then you're good there. So like I said, please practice this algebraic technique, divide by the highest power in the denominator, because we'll use that for something else later on in the year. So I just need you to know that technique. And then after that, if we're just using it to find horizontal asymptotes, then you can use these pre-calc shortcuts that we did last year, right? Where you look at the degree. So remember, if the numerator has a greater than the degree of the denominator, there are no horizontal asymptotes. So that is like number 2 above. if I said, what's the horizontal asymptotes here? You could look at, hey, the degree on the top is larger. I know I'm going to get infinity or negative infinity for that when I do my limit. So I don't have to do the limit. I can just say, hey, there's no horizontal asymptotes there. If the denominator has a bigger degree than the numerator, right? So if the denominator is bigger, it's always going to be y equals 0 is the horizontal asymptote. Your example above is number 3. Number 3, if I gave you that function, said what's the horizontal asymptote, you will be able to look and say, hey, the degree on the bottom is larger. Anytime the degree on the bottom is larger, y equals 0 is the horizontal asymptote. Remember, the definition of a horizontal asymptote is what's that limit as x approaches infinity, and I'm just giving you a shortcut to know what that answer is going to be. And then anytime the numerator and the denominator have the same degree, then you're going to use the leading coefficient. So like right here on number 1, so the example here is number 1, y equals -7/6 is our horizontal asymptote right there. So on number 1, that's so the answer that we got. And notice if I had to do number 1, the shortcut way is, and technically the shortcut works with polynomials, and that's why we learned that technique too, because when you get other weird functions, it's not all polynomials and stuff like that, we got to rely on this algebraic technique. But anyways, so that's what we're getting there. Notice that it's x to the 4th over x to the 4th as the highest degree. So then the leading coefficient is -7/6, and that's the horizontal asymptote right there. So we're going to be using those pre-cal shortcuts when we're doing all of our graphs and stuff like that. So for the second half of the assignment. And if you turn this over, we'll do slant asymptotes. Another name for a slant asymptote is an oblique asymptote. That's when the numerator is exactly 1 larger than the denominator. So like if it's an x to the 4th over x cubed or x cubed over x squared, it'll have a slant asymptote. And then it still won't have any horizontal asymptotes because it'll be larger on the top right there. All right, so let's turn it to the other side. I got a lot of this filled in for you already. Here's what I want us to be able to do is kind of ignore the directions of the book. I want us to graph the function. So no calculator. Graph this thing using an x, y, y prime chart. The next section, we're going to put everything together and we're going to find the second derivative, and we're going to have one giant chart here. So this is just kind of my attempt at somewhat baby steps. They're not like a baby step there because you're doing a lot of good work in this section here, but little mini step before we get to the whole shebang and put everything together. But I want us to graph it. We'll find intercepts if it's easy for us to do so. If it's a little bit crazy for us to do so, then we just won't worry about those. We'll do it without them. But usually it's real easy for us to find the intercepts real quick, so we'll find those. But we got to find any asymptotes, vertical, horizontal, and then in the future it'll be slant. And I want you to find any relative max or relative min. So like increasing, decreasing. So essentially we're going to do like what we did in the x, y, y prime, where we do increasing, decreasing, relative extrema. We're going to make a chart and then we're going to go like try to sketch the graph of this thing. So a reminder what the vertical asymptote is, that's up there for you. So let's look at this example here. So one, you got to do your first derivative. That's it. Don't worry about the second derivative of this section. You just find your first derivative on your own. I already did it for us to save us some time there. And then you set the top and the bottom equal to 0, get your critical number. So -3 and +3, that's where the bottom of that derivative is undefined. So I got undefined there. That's also, if you take that original denominator, set it equal to 0, your vertical asymptotes are x equals 3 and x equals -3. And in the horizontal asymptotes, if you use a shortcut from the front side, the degree on the bottom is larger, which means y equals 0 is that horizontal asymptote right there. Now I'm going to do intercepts. To find the x-intercept, you plug in 0 for y. So if I plug in 0 for that y, remember a fraction equals 0 where the top is equal to 0. So if you set that top equal to 0, you plug in 0 for the y, and if you go 2x equals 0, you're also going to get x equals 0. And then if you find like the y-intercept, you plug in 0 for the x's. But see, if you plug in 0 for the x's, then you do 0 divided by 9, you're also going to get 0. So like that's the origin. That's going to be your x-intercept and your y-intercept. So if it's real quick and easy for us to do the intercepts, let's go ahead and do that. If you find yourself setting it equal to 0 and finding that you need like a P over Q rational root theorem, like that rational root theorem thing, then we're just not going to worry about finding those for right now. We're just going to do the intercepts if they're quick and easy. I don't know what little animal do you see right there? That's an owl right there, right? So you got like the don't, I don't know, you got some little feet. I don't know, maybe some feathers or something. And then you got like the ears. All right, it was looking more like an owl a little bit ago there. And I don't know, it's probably got some fluffy, ruffled feathers or something like that. I don't know, but maybe you could draw a better owl on your homework, and then I kind of see that there. Maybe you got some better artwork than that. That looks pretty horrible. If I was on the board though, I'm telling you, I'll draw a perfect owl, man. It'd be perfect. But anyways, all right. So here's what we're gonna do. What we normally did, right? So you already know all this stuff. We're just take some test points, and we're gonna plug that into the first row. Now, since that bottom is squared, that bottom is always positive. So I don't even need to waste time plugging into there. And then this 2 is always positive. So really, and heck, this is x squared, which is 0 or positive, and you're adding a number to it. So I guess that's always positive too. So I'm noticing that this thing is always positive. I can go ahead and put pluses in there right there. That won't always happen, but you know, you got sometimes just plug in the numbers there, and then you're gonna get that's always positive. And then here, remember, if your first row is positive, that tells us our original function is increasing. So everywhere this function is defined, we know we got a couple asymptotes in there, but everywhere else, it's going to be going uphill. So I got pretty much everything that I need in order to do the graph of this thing. Now, to me, since we already found all the info and I got all my chart already figured out here, to me, this is the fun part of the problem when we go to do the graph there. You have to start with something. I remember I had one girl for help in the morning, and she had all the hardest work done, and then she couldn't do the very end because she was in tears because she didn't have anywhere to start. She didn't put the asymptotes on there. She didn't put the intercepts on there. So if you found the asymptotes, might as well go ahead and put those on there, right? You got x equals 3 and negative 3. And then you also have the y equals 0, the x-axis as your horizontal asymptote right there. And then look what you're going to do from negative infinity to negative 3. So that's to the left of this vertical asymptote. Your function is increasing. I'm telling you, if your function is increasing, that means it's going uphill as you go left to right. You can't draw your hyperbola branch down here because then it would be decreasing. You have to draw your branch like that. And so that's a pretty powerful thing. We're taking this pretty complex equation and we're doing this whole entire graph without even plotting any points there, right? Now I do have an intercept at the origin, so I could put a point there. And then look, in the middle, between your asymptotes here, your derivative is positive, which means your function is increasing. So you got to make it increasing and still approaching those vertical asymptotes, which means as you go left to right, it's got to be going uphill and it's got to approach those vertical asymptotes right there. So it's increasing everywhere. And if you were to have something like, hey, if it did switch to, you know, I had like a 0 and then it went from positive to negative derivative, then it went uphill, downhill. We'll have all scenarios with this stuff there. The signs won't always alternate. We just had that for you right there. And then to the other side, it's still increasing, which means I can't draw my branch here. I have to draw my branch like that. And so you just did a rough sketch that graph. That's all we need using that first derivative. Okay, now in the future, I know this is an inflection point because there's spilling the water and holding the water, but we'll use the second derivative. There are a lot of graphs out there we can do with just the first derivative, and so I'm going to be a little bit careful which problems I'm assigning here. But to do all the graphs, we're going to need the shape of that graph. We're going to need that second derivative as well. All right, so we'll put that all together next time. Now, I would want to mention, I got this little picture up here for you. The definition of a horizontal asymptote is as you approach infinity. So occasionally, you can have a graph cross a horizontal asymptote, and then it'll approach that horizontal asymptote. So, you know, you typically don't see a graph crossing the vertical asymptote, but, you know, notice we cross it right here, but as you're approaching infinity, that's what that graph is approaching right there. So if it crosses, it's going to be for a relatively small value of x, but as you're approaching infinity, it's going to approach that thing. I want you to pause for a second and just think, why did I know that this graph did not do that? Is because one, we didn't have any other intercepts. It didn't cross the x-axis. My intercept work would have given me that. And then two, what you're probably thinking is from 3 to infinity, this function is always increasing. And so if it did do something like this, that means it went from increasing to decrease at some point. So if it did do that, our derivative would have given us another point to check, and it would have that derivative would have went plus to minus on each side of that point right there, and we would have had, you know, that going back downhill for us. But right now we don't have to worry so much about that. We'll fine tune that and we'll put everything together in the next section in addition with the slant asymptotes. So, all right, and that's that. And then, like I said, just please practice as much as you can without the calculus. So we'll be prepared for any sort of college class, and we'll prepare for the AP test there and just know the properties. All right, let's do one final example here. I think we got it. This denominator is never equal to 0, so there are no vertical asymptotes. The degrees are the same, so you're going to use the leading coefficients. Y equals 2 is your horizontal asymptote. if I do a real quick intercept, if I plug in 0 for the x, I get 0 divided by a number, which is 0. And if I plug in 0 for the y, I get x is equal to 0. So 0, 0 again is both my x and the y intercept. I already did the first derivative for you. You got to do that on your own. And then take the top and the bottom, set that equal to 0. It turns out that bottom is never equal to 0. But if I did get a couple numbers there, then you're going to go ahead and do that and put those in on your chart. So x equals 0 is the only number. And then notice that came from the top. So my derivative is equal to 0 there. And that's kind of important to make sure you get the undefineds right there. So you don't, you got to be careful with that. And then I'm going to take these numbers and plug those in for x. So now this bottom is being squared. So that means that the denominator is always positive. So I really just got to plug it into that 16x part. So if I plug in a -1, I get a negative. If I plug in a +1, I'm going to get a positive. And that just tells me my original function switches from decreasing to increasing. So if my graph goes down, then goes back up, that's going to be a relative min, and we got to find it. All right. So when we graph it, we got to find the asymptotes, any extreme, any relative max, relative min. We must find those points and put those on the actual graph. So if I take the 0, plug into the original function, we're going to get 0 for that y value. And then that's pretty much the hardest part right there on these problems, is going to be doing the derivatives. Sometimes the chart gets a little bit messy, especially if I got some trig and stuff involved. But look what happens when we go to the graph. To me, I like this part of the problem. I already did the hardest part of it. I got y equals 2 as the horizontal asymptote. I got 0, 0 for my min. Sometimes I use a little m for a min, a capital M for a max, just in the future. It helps me keep track. I'll put an I there for an inflection point later on. And then from -infinity to 0, your graph is decreasing, and then it switches to increasing. So I got to draw, and I still need to approach those horizontal asymptotes. So I got to draw something like this. It goes downhill, and then at 0, it's going to go uphill. And there's your graph. Now, this is smooth and curvy because my derivative is equal to 0. If your derivative is 0, that means it's smooth and curvy right there. I know, and then that's why this is important, because if that derivative is undefined, then your graph is going to do this, and it's come to a corner point, and then go like that, right? And see that if it went downhill and then uphill, minus and positive first derivative, and that's undefined, that means your derivative doesn't exist, but you still have a point there, right? But I knew it didn't do that because that derivative was, that's where the top was 0, and that should have been smooth and curvy right there. And what I want to stress, one more little thing, is right here and right here, those are 2 inflection points. In this section, we're not worried about finding those. In that next section, we're going to need to find the second derivative. We will have a second derivative row, and we will have points there to find those inflection points there. And the second derivative would have switched from negative to positive to negative to tell us the concave up and concave down stuff right there. So please just practice these as much as possible, and we'll go through stuff. And then I'm probably going to provide my work for all these graphs and stuff like that, so you can kind of work through and figure out a lot of that stuff on your own, and then just let me know if you got some questions there.